Barbara is investigating the relationship between average income and average annual carbon dioxide emissions for different countries. She takes a random sample of 24 countries and finds the product moment correlation coefficient between the average annual CO2 emissions and average income to be 0.446. Part A says we need to state our hypothesis clearly and test at the 5% significance level whether or not the product moment correlation coefficient for all countries is greater than 0. And this is for 3 marks. Firstly, we need to state our hypotheses. So our null hypothesis, so H0, we can say that rho equals 0. Then our alternative hypothesis, so H1, is that rho, and looking back up at the question, we see we're testing whether or not the product moment correlation coefficient is greater than 0. So because it's saying it's greater than 0, our alternative hypothesis is going to be the rho is greater than 0. So the next thing we need to do is find our critical value. So to do that, we're going to use the tables, but we need a bit of information first. So back up in the question, we need the significance level. So it tells us it's at the 5% significance level. We also know it's a sample of 24 countries. So we can say, okay, so n equals 24, so our sample size is 24, and the significance level equals 5%. So what I've got over here is a snippet of the table. So we need to cross-reference it to find our critical value. So going down the sample size column on the right, okay, so we've got sample size of 24, and the significance level, so it's 5%, so that's 0.05 if we're representing a decimal. So we know that our critical value is 0.3438. So now I'm just going to draw out a little line to help us visualize the next bit. So if we imagine in the middle at 0, it goes down to -1 and goes up to 1. Our critical value is 0.3438. I'm going to label that on really roughly, so somewhere like here. And because we're testing, so we're seeing if it's greater than 0, this area here is our critical region. And the product moment correlation coefficient that Barbara found was 0.446. And okay, that's great. 0.446 very roughly falls in here, but we know it's definitely inside the critical region. So we can say that 0.446 is greater than our critical value of 0.3438. So there is evidence that the product moment correlation coefficient is greater than 0. However, if we're in a different scenario and the product moment correlation coefficient was outside of the critical region, then we can say there isn't evidence. So look at the mark scheme. We get 1 mark here for correctly stating our hypotheses. We get another mark here for getting the critical value. And then we get a final mark here for a correct concluding statement such as this. Barbara believes that a non-linear model will be a better fit to the data. She codes the data using m equals log base 10 of x and c equals log base 10 of y, and obtains the model c equals minus 1.82 plus 0.89 m. The product moment correlation coefficient between c and m is found to be 0.882. Part B says we need to explain how this value supports Barbara's belief. Essentially, we need to explain why this value supports that a non-linear model will be a better fit to the data. So I'm going to say here is that the value is closer to 1. So we can see here it was found to be 0.882, but before it was only found to be 0.446. And how the product moment correlation coefficient works, the closer the value is to 1, the stronger the positive correlation is. So in this case, because it's closer to 1, we know that it's likely to have been a better fit to the data. For part B, we get 1 mark here for saying something like the value is closer to 1, or there's a stronger positive correlation, something along those lines. So lastly, we're going to look at part C. So we need to show that the relationship between y and x can be written in the form y equals a multiplied by x to the power of n, where a and n are constants to be found. And this is for 5 marks. So looking back up to the information earlier, we can see, okay, so we've got that c equals minus 1.82 plus 0.89 multiplied by m. And we know that she got to that by using the fact that m equals log base 10 of x and c equals log base 10 of y. So we're going to use this to sort of work backwards. So what I'm going to do is I'm going to replace c with log base 10 of y and replace m with log base 10 of x. So now we've introduced some logs, we can start using our log laws to try and get it down into a form of y equals ax to the power of m. So first I want to get y by itself as the subject, so we need to get rid of this log. So if I raise everything to be a power of 10, so I'm going to do 10 to the power of log base 10y, and then do everything as 10 to the power of, on the other side, so 1.82 plus 0.89 multiplied by log of x Now I'm going to use the fact that so in this case, if we got 10 to the power of log base 10 of something just equals that something. So essentially you can imagine this 10 and this log base 10 cancelling. This works with any base as long as these numbers are the same. So the base is the same as this number here. And look over here on the left hand side, this is the exact situation we've got. So we can essentially say, okay, so that's y equals, and then we're going to keep everything on the right hand side. So 10 to the power of 1.82 plus 0.89 multiplied by log of x. Next, I'm going to split this up using our indice laws. So we know this indice law where we add the powers here, but I'm going to use it in reverse. So I'm actually going to split this up. So I'm going to say y equals 10 to the power of minus 1.82 multiplied by 10 to the power of 0.89 multiplied by log of x. Now I'm going down to the next step. There are a couple of things we can do. So we can now evaluate this in the calculator, which gives us 0.015. Then I'm actually going to use log laws within the power up here. So I'm going to bring this 0.89 up to be the power here. Using this log law here saying that we can sort of bring the power down, or in reverse we can bring the power up. So doing that, I'm going to multiply by 10 power of log base 10 of x to the power of 0.89. Now what we've got ourselves here is in the situation we are earlier, where we've got a 10 to the power of log base 10. So using the same rule here that we did earlier, we can just say, okay, so this is y equals 0.015 multiplied by x power of 0.89. Now we finish the question, we've got it in the form y equals some constant a, so a is 0.015, multiplied by x, the power of some constant n, which in this case is 0.89. So we get 1 mark up here for realising that we can replace c and m. We get another mark for getting down to this line and making y the subject. We get another mark here for both these lines, so realising we can split it up using our indice laws, and then bringing the 0.89 up to be a power. And then we get 2 marks down here for getting both 0.015 and 0.89.